Good morning or good afternoon, everyone. This is Mike Cavanaugh. I'm a senior principal at Geosyntec Consultants in Oakland, and I'm going to be the facilitator of today's webinar on behalf of CERTIP and ESTCP. We have some very exciting topics today. I'm looking forward to it. Hearing from the APTIM Federal Services team. This webinar will consist of a brief overview of CERTIP and ESTCP, followed by the technical portion of the webinar, which features Department of Defense webinar detailing results from Department of funded research on in situ treatment of emerging contaminants to improve the effectiveness and reduce costs for DoD land management. First, Dr. Paul Hatzinger from APTIM Federal Services will elaborate on a novel reactive gas process for the remediation of vadose zone source areas containing 1,2,3-trichloropropane. His presentation will be followed by a Q&A session. And then second, Dr. Paul Koster von Groos from APTIM Federal Services also will discuss evaluating natural attenuation and in situ treatment of 1,2-dibromoethane, EDB, at a complex field site. We will conclude the webinar with a longer Q&A session. On this slide, we've provided a few suggestions in case you experience technical difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use. If you use the content on your screen, or if your screen freezes, try keying Control plus F5 to perform a hard refresh. I'm sure you'll all look forward to that one. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test, Speaker, and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here. People are standing by to help. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions in advance of that session. When submitting your questions, please make sure to add your organization name at the end of your question so that we can identify you during the Q&A sessions. With that, I think I'd like to introduce Dr. Andrea Leeson, but Andrea may be have some difficulties in getting here. Let's see, is Andrea on the line? Apparently not. All right, well, so I'm going to sub today for Andrea and do my best in following up. So if we go to slide 9. As you can see on here, this is a summary of the CERTIP ESTC programs. CERTIP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. CERTIP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERTIP funds from both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management decisions. Next slide. Oh, sorry, don't move forward here. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERTIP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERTIP and ESTCP are complementary programs with much of CERTIP research occurring at the lab and pilot scale, occasional field efforts, while ESTCP demonstrations are primarily at the pilot and the field scale, although occasionally supporting lab efforts are conducted. So on slide 14, you can find more information about upcoming webinars at this link. Registration is now live for webinars through the end of the year. I'd like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate if you could please take a moment to complete the survey that will pop up on your screen at the end of the webcast. So if we go to slide 15, I'm pleased to announce that CERDUP ESTC Symposium will be held for the second year in a row this upcoming December, I think, in Washington, D.C. It says December 3-5. The three-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available on the CERDUP and ESTC website. And on behalf of Andrea, I think she hopes that you all enjoy the webinar today. So with that, let me go back to my facilitator hat and introduce Paul Hatzinger from APTIM. Paul is the Director of the Biotechnology Development and Applications Group at APTIM Federal Services in New Jersey. Paul is a broadly trained environmental scientist with expertise in groundwater microbiology and geochemistry, bioremediation, and stable isotope analyses. His current areas of research include the development of in situ and ex situ remediation strategies for emerging groundwater contaminants, including 1,2,3-trichloropropane, 1,4-dioxane, traditional and insensitive munitions constituents, NDMA, and 1,2-dibromoethane. Paul has a bachelor's degree in biology and environmental science from St. Lawrence University and a master's and doctoral degrees in environmental toxicology from Cornell University. It's been a pleasure to work with Paul over the years. So Paul, take it over.
Great, thanks a lot, Mike. So I'm going to talk about an interesting process to treat TCP, or 1,2,3-trichloropropane, in vadose zone soils. I'd like to first acknowledge collaborators on this project, which is funded through ESTCP, and that includes Chuck Coyle, Scott Weisner, and Mandy Michelson from the Army Corps, as well as Greg Lavorgny and Paul Koster van Groos from APTIM. Now, a little bit about what we're going to talk about today. I'm going to talk about the issue with TCP, a little bit of background about where it comes from, this process that we're looking at, that we're developing to treat this in vadose soils in particular, which we know it's challenging to treat anything in the vadose zone. I'm going to go through some laboratory study results and then a bit of field investigation data. Now, we aren't in the field yet, so I'll talk about our demonstration design, kind of what we're going to do moving forward, and then wrap up with a couple of conclusions. Now, TCP, pretty simple molecule. We see that on the right, 3 carbons, 3 chlorines. It is on the Unregulated Contaminant Monitoring Rule, List 3. That's an EPA list. That's an emerging contaminant list, but it doesn't currently have a federal MCL. Interestingly, California established an MCL, the California State Water Resources Control Board, in December of 2017, and that MCL is only 5 parts per trillion. So, you know, we worry about PFAS at 70, trichloropropane, because of its potential carcinogenicity, is now regulated in California at 5 ppt. And if you go to the website, the California Water Board's website, they've been tracking through 2018 the number of exceedances in drinking water. And believe it or not, that's 569 drinking water sources have had TCP hits at over 5 parts per trillion, and more than half of those are over 20 parts per trillion. So where does this come from? Well, within DoD, it's been used as a solvent for cleaning, degreasing, varnish removal. It's used in aircraft tank sealers. But probably more importantly, in some of these areas, it was a contaminant in a common soil fumigant called DD, which is a mixture of 1,3-dichloropropene and 1,2-dichloropropane. That's no longer sold, but there is a fumigant called Telone 2, which is mostly 1,3-dichloropropene, which also contains TCP. Now, the DoD has looked for this at some various bases. They found 1,400 wells, or about 17%, had detectable levels. And in soil borings, there was about a 7% rate in surface soils. So some of its characteristics in this chart shows a comparison to some chemicals we're used to looking at, TCE and carbon tetrachloride. What we see is that its vapor pressure and its Henry's law constant are lower than those two, so it is less volatile. It's quite soluble, more soluble than either TCE or carbon tet, and it's got a log KOC that's about the same, about 2.5. So it's somewhat difficult to airstrip or volatilize from water. It's also non-reactive with a lot of the types of things that we use in this industry, things like zero-valent iron, potassium permanganate. So it's hard to treat that way. It's a pretty recalcitrant compound. Now, there is some evidence of both reductive dechlorination. So anaerobically, dihalogenamonas is an organism that can actually use this as an electron acceptor. And there's been some studies on co-metabolism, so organisms that can use ammonia, propane, or methane can actually degrade this aerobically. It's also reactive with some strong oxidants like activated persulfate and some very strong reductants like zero-valent zinc. However, what we're going to be talking about today in vadose is the fact that this compound is subject to alkaline hydrolysis. So what we're going to try to do in the field is we're going to try to increase the pH of soil in the vadose zone. And to do that, having something that's gaseous is important. And as it turns out, if you inject gaseous ammonia, so NH3, into soils or water, you can see it will react with the water to form ammonium, NH4+, and hydroxide ion, thus increasing the pH of that environment. So essentially then, if you have a 5% ammonia in air in a water environment, you'll get about 3 molar ammonia in solution, and you can get a pH almost up to 12, so higher than 11.5. So the concept here then is to go to the vadose zone, inject ammonia into the vadose zone, and create hydroxyl radical and increase pH. Now, when you do that, and this is some work by Paul Tratniak's group, and he had some CERTUP funding going back a number of years and did some great fundamental work on some of the abiotic reaction mechanisms of TCP. But essentially, TCP will undergo what appears to be a two-step reaction. It's sort of an elimination reaction followed by hydrolysis. You lose 2 chlorines, and then you end up with this interesting molecule, which is actually also called 2-chloroallyl alcohol. And if you look back in the literature to the early 1990s, a laboratory, a gentleman named Dick Jansen, who's pretty well known, isolated a number of organisms that can actually remove that last chlorine and essentially mineralize this. So once you get to this point, this is a readily biodegradable molecule under aerobic conditions. So again, this is some work out of Paul Tratniak's lab, and what he did here in terms of hydrolysis is he took a look at pH. So this is hydrolysis of TCP, and we see we have increasing pH on the x-axis, and then rates, and we'll look at half-life here. So as we go up on the y-axis, the half-life is essentially getting shorter and shorter. So the molecule is breaking down faster and faster. And these different lines, as we move up, are temperatures. So what we see is TCP, in terms of hydrolysis, is affected by both temperature and pH. And with increasing pH, we see that this has a shorter and shorter half-life down into as we get into that 11 or 12 range, we're into a half-life of days. And if we could also increase the temperature, it's very, very short-lived. So you can think about both an alkaline hydrolysis and or a thermal approach, or a combination of the two, essentially to treat TCP in the environment. Now, the site that we're going to be working at is the Brown and Bryant Superfund site. This is in Arvin, California, in the San Joaquin Valley. And this site was a pesticide reformulator from about 1960 to 1989. A lot of materials were mixed here, produced, and spilled, as it turns out. This was added to the Superfund list in 1989, and there's a variety of different contaminants at this location. TCP is one of them. There's also dibromoethane, which Paul Koster Van Groos is going to talk about in the next part of this. There's dibromochloropropane, there's Dynaseb, 1,2-dichloropropane, 1,3-dichloropropane. So a variety of different fumigants, and pesticides. Now this site was, a RCRA cap was put on this site in the 1990s, and sort of a non-RCRA cap to the north was put on as well, just to sort of contain the contamination that's here in the vadose zone. And there's been a variety of different remediation efforts that have been going on at this site over time. Now, our work started with some laboratory studies, and both batch studies and column studies were done. And these were done at the ERDIC lab of the Army Corps of Engineers. And essentially in the batch studies, contaminated soil was collected. It was treated with ammonia gas, increase the pH of the soil, and then look at degradation of, in this case, it was TCP and DCP from the B&B site. I'm also going to show one slide on degradation of RDX in particular, just to show that this approach may be applicable, not only for the contaminant I'm talking about, but some other contaminants of DoD interest. Now, the second set of slides were some column studies, and the objective of these was to look at sort of as a function of ammonia concentration as well as flow rate, sort of how far along a column we could increase the pH of the soils and how long that took and what kind of variables impacted that. So in terms of the batch results, this was the B&B soil. It was remixed with some of the contaminants. They are volatile enough that you can lose them during mixing, et cetera. And then at two different temperatures, 23 and 62 degrees, the soils were incubated either with nothing or with ammonia. And essentially what we see here in the graph is that in our controls at either 23 degrees or 62 degrees, we have a soil pH of around 8. However, once the ammonia is added, we see that we're getting up to just below 11. Now, that's not as high as I had mentioned in my earlier slide, where you can get up in the mid 11s or higher. But I'll talk about that. There's kind of some interesting things at this site which may limit the maximum pH that you can achieve with this approach. Now, if we look at some data from this study, what we see are three compounds, 1,2 and 1,3-dichloropropane, as well as the TCP, the compound of interest here. Now, all of these compounds are subject to alkaline hydrolysis. We look at control samples and then samples extracted after treatment with ammonia. We see at 23 degrees, we have a statistically significant loss there. It ended up for the TCP being on the order of 40%, and this was repeated, and it was as high as 65% loss. And then at higher temperatures, that loss is even greater, so greater than 90%. So again, we have this combination of pH and temperature that controls rates, and that's borne out in the treatability work. I mentioned RDX, and I'm just going to sort of divert one slide here. And in this case, some samples were collected from the Umatilla chemical depot, RDX contaminated soils, and the same sort of approach was used in batch. And we see, again, different soil matrix. We see controls, and then we see the ammonia-treated soil. We see the pH getting up in the 11 range. And if we look at the graph on the left, here's our control sample. And then we see it, the decline in RDX at both 23 and 60 degrees, down to very, very close to detection. So again, this is another approach where you can stimulate alkaline hydrolysis, in this case of RDX as an explosive. And I have a reference. This is some published work. Chuck Coyle is the lead author, and I have references at the end of this presentation where you can look at this material, as well as some information from Paul Tratniak's lab. So now I'll go to the column studies, and The basic idea in these studies, and these were done at the ERDIC lab, is to take a look at different concentrations of ammonia and how far, when you add that in at either 5 or 9.5%, sort of how far that moves in a series of columns. And we can see that these columns were set up in series, but this is sort of one continuous, you can sort of look at this as one, it's not, instead of one long column, there were several columns used, but they're all in series. So, you know, column 1, 2, 3, the gas flows through all of them, and then you can sort of look at the distance that the gas moves and what kind of pH increase you see over time. So this table shows some of the different treatments, and essentially what we were trying to do here is look at a combination of ammonia concentration in air, flow rate, and then there was other variable was moisture content of the soil. So this 16%-ish was the actual content that the soils came out of the site when they were removed through drilling. And essentially then what we did is we said, okay, let's look at, in this case, if we look at number 3 and number 4, the only variable here that's different is the amount of ammonia in air that's added to the columns. And I'm gonna kind of focus on those two. If we look at column 5, the difference here was, so this was very similar to 4, except the moisture content of the soil was a drier soil. And then in column 2, the flow rate was a bit slower. But I'm going to focus mostly here on 3 and 4, which the main difference here was the concentration of ammonia. Now I should note, so when you sort of question, well, how do you pick a concentration? You know, the one thing you have to be cognizant of with ammonia is you know that it is an explosive gas, so you have to understand the upper and lower explosive limit. And the lower explosive limit is about 16%. Upper explosive limit is about 25%. So obviously we want to stay well below that limit. So as we look at the data, what's important here is, first of all, we were able to achieve a pH of greater than 10, and this is just extracted in DI water or with some calcium chloride. They're just soil extraction methods. So these columns were taken apart. They were treated for about 2 weeks. Taken apart, and subsamples were taken looking at pH. In terms of the 5% versus the 9.5% ammonia, so column 3 was 5%, 4 was 9.5%. What we see is that the total amount of ammonia that was residual in the soil upon extraction was a lot less in the 5% than the 9.5%, which makes some sense. But the amount of soil that was treated was actually greater in the 5%, and also the distance in the column was greater, so that also makes sense. So we reached basically the same pH in these two columns, but we had a lot less residual ammonia, and our treatment distance was much farther. So that sort of guided us in terms of what we're likely to do in the field. We use a lower ammonia concentration. We can still achieve the pHs. You know, we're not going to see much difference between the two, but our distance should be much greater. The only other point to note, which also makes a lot of sense, is that when the soil moisture is lower, your treatment distance, you know, is also much, much greater because there's less water for the ammonia to saturate as it sort of moves along on the path. Now, this was a little bit of modeling done by Scott Weisner, and one of the things we wanted to make sure of is that we can get enough of a treatment radius when we go to the field. So basically he did some modeling, and essentially the units have changed here, but this is just the flow rate of 5% ammonia gas through the soils, and then the radius treated in feet. And we can see that as we do this, you know, these are pretty low flow rates, you know, 0.3 to 1.4 cubic feet per minute. We can get systems that can even go much higher than that. But essentially, even at a very low flow rate, you know, over about a year, you'll have a 15-foot radius, and you can get well beyond that. So that suggests that this approach should cover enough of a radius that, in fact, you can, you know, you could implement it at a reasonable scale. Now, one of the things that I mentioned early on was that we weren't really achieving that pH of 11.5 to 12 that you see in some of the modeling. And I think one of the reasons for that is it turns out at this B&B site, there was a buried tank of anhydrous ammonia at the site that must have ruptured at some point in time. So you have starting ammonia levels in the soil, so NH4 plus, on the order of 300 to as much as 3,000 or 4,000 milligrams per kilogram. So you have gram per kilogram levels of ammonia. And it turns out if you sort of take a look at the chemistry of this, when you have a large amount of ammonia in the soil and you're adding NH3, you already sort of have this warehouse full that's already in the water phase, and it turns out that impacts your upper pH. And Paul Koster van Groos did some modeling which also confirmed this. So we were seeing those pH values in our studies of around 10.2, 10.3, 10.4 rather than in the mid-11s, and that seems to be the reason for that. Now, the EPA is doing some additional investigation work at the site, looking for TCP and Dynaseb, which is also a contaminant of significant concern. And our group also went out and did some drilling. So there's been a lot of drilling going on at the B&B site over the past year. On the left, we have just a sort of a typical vadose zone core log. You see you've got sort of silty sand, some silt and sand, and then kind of this mixed, silty sand, silty fines. The geologists tell me this is all, amenable to adding gas. And then you hit a layer at anywhere from like 45 to 55 feet that our geologists sort of describe as lean clay. It's also been described as caliche, but it's sort of an impenetrable layer. So we're sort of working above that in the vadose zone, sort of above that zone. Now, if you go out and you look at the different cores that we're taking here, and each of these yellow points is a core, you see we have TCP contamination down. This was an old pesticide washout area that overflowed multiple times. This was an area historically that had high TCP, and we see again some hits in 30,000 range, so 30 ppb, 43 ppb, and this is north of the RCRA cap, but this again is still a capped paved area. So you've got it sort of throughout the site with some particularly high concentrations sort of up in this region. Now, when EPA was doing this drilling, and APTIM is a support contractor on this, as well as when we were doing some of our drilling, we also looked at ammonia concentrations and pH. And one of the things that was very interesting here is that when you looked at TCP concentration versus ammonia, there was a bit of a relationship. And as that ammonia increased, and again, this is probably from that ruptured anhydrous tank or other spills, you see as ammonia increases, TCP decreases. And on the other side, on the right, basically as pH of the soil increases, TCP decreases. Now, this could be fortuitous based upon the way these contaminants were spilled, but also over a period of 30, 40, 50 years, this may actually reflect an attenuation of TCP based upon hydrolysis over time with this increasing pH. And there's no similar relationships with Dynaseb, which is not subject to alkaline hydrolysis, but is also throughout this site. So I thought that was just an interesting relationship to take a look at. So then just finishing up with our demo design. So what we plan to do is build an ammonia injection trailer, put in 3 gas injection wells, and then a series of vapor monitoring points. So we'll be taking vapor samples. We'll also be doing some drilling and taking cores throughout the process. And we'll have some shallow vapor probes because we'll be looking for any fugitive ammonia coming up through the vadose zone. We'll also have 1 groundwater well that we'll sample, in particular for any ammonia or nitrate that may reach groundwater, although we don't expect that to happen. Just a quick, simple flow diagram. The system will be more complex than this, and Greg Lavorny in our group has designed a number of similar types of systems. We do a lot of work with co-metabolism, where again you're adding a gas, a flammable gas, something like propane or methane or ethane. So we understand the safety measures that need to go into this, spark arresters and other things. But essentially you'll have compressed air and anhydrous, which will be moving through a series of valves into our vadose zone injection wells. In terms of our demo schedule, we've just wrapped up the treatability work, and we'll be submitting that report this month. We're going to have a baseline phase for about 3 months where we'll take soil cores, we'll take gas samples, we'll also do some groundwater sampling. So we'll look in our treatment area, what are the baseline levels. Then we'll have an active treatment phase where we'll be adding ammonia gas, for about 8 months. We'll do monthly soil gas sampling. We'll also, again, take cores and extract them for TCP and these other contaminants. And then we'll do about 4 months of post-monitoring. So once we've stopped adding the ammonia, and again, this also gives us an additional residence time to allow treatment to occur. And at the end of this, again, we'll take some soil cores and then decommission. So it's about a 15-month project. So I'll wrap up then. So what are the conclusions from this? Ammonia gas increases soil pH, and it promotes contaminant hydrolysis. And this is particularly useful for unsaturated zones. And, you know, increasing pH with gases is somewhat difficult. And we know that treating contaminants in the vadose zone biologically or abiotically has a lot of challenges. This will be effective for DOD contaminants, things like TCP and DCP, as well as explosives. And there are others, chloroform, there are some chlorinateds, EDB, dibromoethane from fuels that Paul will talk about, is also amenable to this process. Here are some of the references I discussed. The first sort of talks about some of the DOD occurrence data. And then in terms of abiotic degradation, this is a paper from Paul Tratniak's group, again, CERDUP funded work. And then a paper from Chuck Coyle and the group at ERDIC looking at the use of ammonia gas for TCP and explosives. I recommend that you take a look at those if you have more interest. And with that, if you have questions beyond this, please feel free to email me or give me a call. And I'll conclude there.
Paul, thank you very much. This is Mike Cavanaugh again. We do have about 10 minutes for some questions, and a number of questions have come in. I'm going to read them off, Paul, and let you have a chance to respond. The first one is, would injecting ammonia in the saturated zone degrade 1,2,3 TCP in groundwater?
Yeah, Mike, good question. I don't think this is probably an approach that you would want to use in water. I think there are other alternatives for TCP that make more sense. As I mentioned, in a higher concentration area, this is subject to the type of reductive dechlorination that, that we use for chlorinated solvents. So that's a possibility. For lower concentrations, there's the possibility to do co-metabolic treatment. With things like, there was just a paper published a year or two ago that propane can stimulate co-metabolism of TCP, as can methane. And then a few, stronger oxidants are a possibility as well. But, there are some commercial anaerobic cultures and some aerobic cultures as well that you might take a look at. I think that's probably a better approach than trying this in water, just because you need a lot of ammonia. You're going to create a lot of nitrate through nitrification and other processes. I think this is much better suited for unsaturated environments.
Great, thank you. You talked about RDX. Are there some other contaminants that you think this approach in the vadose zone using ammonia or other gases might work? I know there's been other techniques used for chlorate, for example.
Yeah, well, one interesting sort of technology that is being looked at is actually up at Pacific Northwest National Lab. So the DOE sort of just on a separate route, two separate paths, started looking at this same approach to increase soil pH to immobilize uranium. They have a lot of issues of a deep vadose zone heavily contaminated with uranium, and they looked at injecting ammonia gas to immobilize uranium, but the mechanism is quite different. Rather than a hydrolysis mechanism like we see for TCP, if you can get the pH of some soils high enough, you can actually start dissolving silica and some of the other minerals, and as the pH then comes back down, they can trap the uranium and immobilize it. So there may be some potential for vadose zone treatment of mobile metals with this. It's not something we're looking at, but it's something PNNL has done quite a bit of work on, and there are some, if you just sort of look up, ammonia gas hydrolysis online, or ammonia gas and uranium, you'll see some papers and some reports by PNNL. Jim Sicotti is one of the folks that's the scientist that's involved with that. and Mike Truex.
Great. Okay, another question. Is this a combined sort of physical, chemical, microbially mediated degradation pathway? I mean, in other words, you see hydrolysis, but are you also, is it going to be worthwhile to try to understand the microbial populations associated with this, with these reactions?
Yeah, you know, it could, Mike, and the one place where that could be very interesting is there's an old paper, it must be in the 80s or early 90s. It was some of Mike Hyman's work. He looked at he looked at co-metabolism of a variety of different chlorinatids by ammonia monooxygenase, and that's the enzyme that nitrifying bacteria use to basically start the oxidative pathway from ammonia through to nitrate. It's the first step in that. Takes ammonia to hydroxylamine, but it's a broad specificity enzyme, and it turned out that he showed that co-metabolizes trichloropropane along with a variety of other compounds. Now, the rates appear to be fairly slow, but if we're adding ammonia to the soils, or there's already ammonia existing like there is at the B&B site, it's possible that under sort of more normal pH conditions, 7, 8, like you see at the site, that you may be getting some nitrifiers that are actually co-metabolizing TCP just using ammonia that's already in the soils. And in fact, we do have another sort of treatability study going on in our lab where we're trying to document that process. We haven't seen a lot of nitrification in the B&B soils or a lot of evidence of ammonia monooxygenase, and it could be that these ammonia concentrations are just extremely high here compared to normal environments when you're at the 2,000 to 3,000 ppm range. But yeah, interesting thought. Okay.
Good. One of the issues that's probably critical to success is this radius of influence. Could you talk a little bit more about what you're anticipating in the field related to permeability and such? I certainly did some modeling. Could you elaborate on that a little bit more?
Yeah, that's just going to be, one of the concerns, I'll be honest with you, was the opposite, which is, fugitive ammonia. So one of the early, as we sort of started talking to regulatory folks about this, one of the larger concerns as well is this ammonia going to move through, basically some more permeable paths and sort of leave your zone of influence. So the bigger concern is that it's going to move too far. Our concern starting out was that we're not going to be able to move it far enough out in the formation. So you kind of see both sides of that story. But, we're going to try to design our system so that we can get flow rates as high as, 10 standard cubic feet per minute, which should allow us over a reasonably short time to reach about a 20-foot radius of influence. We don't want to necessarily go much further than that. It's a small scale demo. And we will have some outside monitoring if we do see ammonia that's moving beyond our zone, where, we'll shut the system down and take a look at that to make sure that, things aren't moving further than we'd like. But as a small scale demo, if we can get a 15 or 20 foot radius of influence, we think that's perfectly practical if you're going to go do this in the field as a barrier or some other approach. And, that's also what we kind of use in the remediation world when we're injecting things. If you can move something, 15 or 20 feet, that usually becomes a practical size of a larger scale remediation.
Right. It's a good rule of thumb. We had one other broad question. You didn't really state this, I don't think, but I think the general sense is that vadose zone treatment using gaseous techniques is generally quite challenging, and maybe vadose zone in general, especially if you consider the DOE's experience. Is there some fundamental reasons why it is so challenging to go after the vadose zone?
Yeah, I think that's probably a book that could be a Mike Kavanaugh edited ESTCP book. But Yeah, I think there's a lot of reasons. And, preferential flow obviously is a concern. When we try to do this biologically, soil moisture is an issue, which again is one reason that we're trying to approach this abiotically. I'm not aware. I know Pat Evans did some work with perchlorate where he was injecting some gaseous substrates, but you tend to dry the environment out further. Those are just that's the biological challenge. The abiotic challenge, I think, is preferential flow paths. We know that that's an issue, and those are some of the things that we're going to have to think about and look for as we sample. And we will have our sampling apparatus at different depths and try to understand how well we did with this approach. But yeah, it's a very challenging environment, as you know.
Well, Paul, thank you very much. I think we'll call it quits on questions for you. There are a few others. I would encourage the participants in today's seminar to contact Paul directly, and good luck with the field demonstration.
Great, thank you.
All right, the second portion of today's presentation will be delivered by another member of the APTIM Federal Services Group, and it's Dr. Paul Koster von Groos. He's a research scientist in Lawrenceville, New Jersey, and his research focuses on quantifying environmental processes with respect to natural attenuation, remediation, and forensics, and on developing novel in situ and ex situ treatment technologies. Since joining APTIM, Paul's work has included a focus on emerging contaminants. He earned a bachelor's degree in civil and environmental engineering from Cornell, a master's degree in environmental engineering from the University of Michigan, and a doctoral degree in environmental engineering from the University of California, Berkeley. So he moved clearly from the east to west. Paul, please take it from here.
Right, and now I'm back east. Thank you, Mike. And thanks everyone for taking the time to tune in. Before I get started, let me acknowledge our partners in this. We worked with the University of Oklahoma to do some isotope analyses. That was very important for this work. And this work was funded through the ESTCP program as well. I'm going to be discussing some of our experience with dibromoethane, or EDB, especially with respect to natural attenuation and in situ treatment, in this case, anaerobic biostimulation at a complex field site. And this has been a great project, so I'm excited to share some of our results with you. So this is sort of a roadmap of what I'll be talking about. I'll be giving a little bit of project background and describe why we're interested in EDB. And then I'll talk about our isotope studies and then how those were important and how we are able to use isotopes in this context. And that context is to look at natural attenuation of the EDB and anaerobic biostimulation at our field site, the site we were at, and that was Kirtland Air Force Base in New Mexico. And then I'll provide some conclusions and describe some benefits to the DoD and I guess the broader audience in general. So EDB is also 1,2-dibromoethane. You see here on the right, it is a brominated analog to 1,2-dichloroethane. So instead of chlorines, you see bromines on this ethane molecule. And we're talking about it here in the context of emerging contaminants, but perhaps like many emerging contaminants, it might be wise to put quotes on emerging because we've known about the toxicity, certainly of EDB for a while, and we've been using it for a very long time. EDB's mostly been used as a fuel additive in leaded gas, and it really started a long time with when we started adding tetraethyl lead to gasoline, which is around the 1920s. And when tetraethyl lead was added to gasoline, and that time it was to boost the octane content and prevent knocking, and you could use more powerful, higher compression engines. But a challenge was that the lead could form lead oxides and foul up your engine, and you wouldn't be running for very long. So lead scavengers like EDB were added to the fuel, and they would help volatilize the lead and remove it from the engine and then into the environment. Another large use of EDB, although much less, so the lead scavenger was about 90% of total EDB use. Agricultural uses were most of the remainder. It was used as a fumigant, and that ended in the early 1980s when people started appreciating the toxicity of EDB more. And so that use was ended and it was banned by the EPA. And then as well, during the 1980s, we stopped using leaded gasoline, so EDB use fell greatly. And then in 1992, the EPA, and so this is recognizing that, we have known about its toxicity for a while, set a federal MCL of 50 parts per trillion. And I'll note that that's the second lowest MCL, second only to dioxin. So, it's certainly something to be concerned about in the environment. But one challenge has been in gasoline locations, it's not something that's really been measured for at those low levels. The typical analyses one does when closing a UST, for example, is an 8260, and you're a couple orders of magnitude higher than the MCL in that case. And in case you thought we stopped using leaded fuels in the 80s, however, we still use leaded fuels in general aviation quite a bit. Here on the right, you see a picture of a Cessna that would use EDB in aviation gas. In late 2008 or so, we were using on the order of 700 million liters of avgas a year. And each one of those liters would hold about 500 milligrams of EDB. So you see a drum here of avgas on the lower right, and that's avgas 100LL. The LL stands for low level lead. But even so, you would have 500 milligrams of EDB per liter. So the Cessna, which has about a 40-gallon tank, would contain about 75 grams of EDB, and that's enough to bring 500 Olympic-sized pools up to the MCL. So it's something to keep in mind that we are certainly still using this compound in a commodity in pretty large volumes. So to provide a little bit of background on this tool that we are using for our project, Isotopes, we're talking about compound-specific isotope analysis, or CSIA. And the compound we're interested in is EDB, so we separate that out, and the isotopes that we've looked at are carbon-12 and carbon-13. The difference in the isotopes are the number of neutrons, so carbon-13 has 7 neutrons, carbon-12 has 6. And their abundances are pretty much that most of the carbon is carbon-12, 99%, and about 1% is carbon-13. But something to note is that the kinetics can be slightly different depending on the isotopic composition, so carbon-13 containing EDB degrades slightly slower than the carbon-12, and the result is that as EDB degrades, the EDB slowly becomes enriched in the heavier isotope, or the carbon-13. So I'm showing that here on the lower right. This is following a Rayleigh fractionation plot, and if you move from right to left on the x-axis, then your EDB is degrading, and on the y-axis you see this value of delta 13C. That really is a measure of the 13C content of the EDB, and as you degrade, you get enriched and you get a more positive value here. Now, I'll also note that there's this epsilon value here that's part of the equation. This epsilon value is different for different reactions, and so it's important to know what this epsilon is to be able to understand how you might use these isotope data in the field. But certainly, any change in isotope composition can give you a good indicator that there has been degradation or transformation of the compound you're looking at. So one thing that we did is we did some lab studies to try to evaluate what these epsilon values might be for EDB, and I'm giving an example here. We did several studies looking at biodegradation, both aerobic and anaerobic. In the upper right, the blue lines show co-metabolic degradation of EDB, and the red lines show anaerobic degradation. That's really what I'll focus on with this slide. We looked at 4 cultures of anaerobic EDB degraders, and each one of these degraded the EDB to ethene and a little bit of ethane and bromine coming off bromide. And you'll see that happens at a variety of timescales, depending on the culture and its content of dehalogenating organisms. But in this case, going from about 3 hours to 12 hours. Note that many of these cultures contain dihalococoides, but there are many other dehalogenating organisms that can dehalogenate EDB. Now, on the lower plot, I'm showing this sort of Rayleigh fractionation that I mentioned before. And what's interesting here is that you'll note that 3 of the cultures sort of collapse onto one line with one epsilon value of about -8. And then this other one, this PGKS culture, has a greater fractionation of about -20. So it gives you some range of what might be happening anaerobically with biodegradation. And one way you would use this information perhaps in the field is you could go and you would evaluate and you make a measurement of about -10 per mil, and then you could go back and say, well, if I know the process was anaerobic biodegradation, then perhaps 80% of the EDB has degraded. So we performed several of these lab studies. We looked at both biological degradation and abiotic degradation. As far as abiotic degradation, we looked at degradation facilitated by iron sulfide minerals, and that seemed to work quite well. And we also evaluated the process of hydrolysis, neutral hydrolysis in this case, so it wasn't base catalyzed, but it was neutral at a variety of temperatures. And we'll note that those occurred with pretty high epsilon values. So this is a linearized version of that Rayleigh plot, and the steeper slope shows a larger extent of fractionation for a given extent of degradation. And then we also looked at co-metabolic degradation that fractionated the isotopes less, and really the anaerobic biodegradation. Most of it occurred a little bit more than aerobic biodegradation, but there was this one culture again that showed greater fractionation. I want to talk a little bit more about this hydrolysis at the site because EDB has been used since the 1920s. It was used extensively in motor vehicle gasoline, leaded gasoline until the 70s and 80s, and continuing in avgas. So it's been potentially in the water for a long time. And the timescale of hydrolysis is about a decade half-life at field temperatures. Of course, it's a function of temperature, so it'll be different in New Mexico at our field site than it is in Maine. But of course, this is occurring, it's pretty much ubiquitous in water, and so it can give you a fair amount of information. You know the kinetics reasonably well because you know the temperature of the water. That's fairly easy to measure. And we saw consistent isotope fractionation for hydrolysis with an epsilon of about -20. And what that allows you to do is it allows you to extrapolate from sort of these experimental temperatures towards field temperatures. And if you were at a field temperature of about 20 degrees centigrade, that would mean that you would be fractionating your carbon-13 by about 1 per mil per year. And so if you had a release in 1979, 40 years ago, that might mean that at a minimum, you would expect the EDB, if it's been in water since that time, to have fractionated by 40 per mil, which is a very significant amount of fractionation that is certainly measurable in the field. So that can help constrain some timing of your release and what's going on. So here's our field site. We're talking about Kirtland Air Force Base. This is just adjacent really to Albuquerque, New Mexico, adjacent to the Albuquerque airport. There was a historic leak of avgas, aviation gas, JP4 and JP8. I believe this was discovered around the turn of the century, but avgas was last used at the site in the mid-1970s, so it must have been occurring for some time previously. And on the right here, you see this large groundwater plume. It's about a mile long, and it flows to the north-northeast. I'll note that most of this plume has EDB concentrations below 1 part per billion. So it's still well above the MCL, but quite low. And most traditional analytical methods, 8260 methods, would not detect this, certainly with the high background of other VOCs. So you have to use a special method 8011 to see these concentrations. But at the site, again, avgas was last used in the 1970s. And the leak was discovered around the turn of the century, and EDB has been measured often at levels of 100 parts per billion or so or more. Now, another thing I'll note here is that avgas was used until the mid-1970s, so in some ways this could be perhaps a good analog to the use of leaded fuels in general, because that was also starting to be phased out around that time period. So, where leaded fuels may have been used, this might be a similar kind of circumstance. Another challenge at the site is the depth to groundwater, which is on the order of 500 feet, and it has been changing with time, and that is certainly a challenge in doing field work. So we were looking at the site in the context of natural attenuation, and so that's looking at the full plume, and then we were also evaluating in situ treatment options, and what we evaluated was an anaerobic biostimulation approach in this sort of lower, higher concentration area that I've highlighted in red. Now, during our work, one thing we were considering was using bromide as a tracer, but we and others thought that it would be important to see if bromide might provide some extra information about the EDB under natural attenuation situations. So we decided to evaluate that before we started adding large concentrations of bromide as a tracer. And it turns out that if you only looked at bromide, it might be difficult to evaluate differences between sources and down gradient because there is this wide range of unimpacted concentrations of bromide from near zero to 2 or 3 parts per million. But if you normalize it by looking at the chloride concentrations, and you can look at this ratio of bromide to chloride, you can see that there really are circumstances, certainly in the source areas, where bromide is enriched beyond what you might expect. So this provides perhaps a nice additional tool and evidence that there is debromination of EDB occurring at the site. And this was very interesting in general. Now I note that EDB degrades anaerobically to ethene, ethane, and bromide. So we also looked at reduced gases such as ethene and ethane. And on this plot, I'm showing in the box the area where the conditions were anaerobic, and they were driven anaerobic by these large hydrocarbon fuel releases. And you see this nice sort of matching between this excess bromide metric and ethene and ethane metric of degradation. That's almost stoichiometric in many cases. So that was quite encouraging and suggests that there is some EDB degradation occurring in these anaerobic conditions at the site. And I'll also note here that those concentrations are much higher than the EDB concentrations, which are shown here in green. And so that shows that perhaps there might be quite a large extent of natural attenuation happening due to this petroleum release at the site. So now moving on to our isotope data, this really excited us because we saw very large shifts in the isotope composition of EDB. And as I mentioned, that is a clear indicator of degradation. We were worried that because concentrations are so low, on the order of a part per billion or less, we lose some analytical precision in measuring the isotope composition. So we were worried that we might not see much, but these values are so large that there really is a very large signal of EDB degradation at the site. So I'll split this into two parts, really looking at a down gradient part with the low concentrations of EDB, and then talk about the source area somewhat as well. We think that this hydrolysis method process that I spoke about earlier might be quite important at these low concentrations down gradient. What I've added here is this red dashed line on the right, and up here at the top, these are the delta 13C values with distance and with groundwater flow. And I've added a characteristic groundwater flow at the site, a characteristic half-life, and our epsilon, our fractionation factor, and you would follow this red dashed line. And that seems very consistent and can explain a lot of the carbon isotope changes you see at the site. So that seems very consistent to hydrolysis, which you think is ubiquitous, is happening at the site. You see some cases where there's more, a greater extent of fractionation. This could be because they are sort of side gradient and it took the EDB a little bit longer to get there, or also there may be other processes that have helped fractionate that further. Now, on the lower graph here, you see EDB concentrations with distance. And again, the dashed line shows the sort of 10-year half-life of EDB and how that would go down gradient. And again, that's fairly consistent with the field data. So that was quite encouraging and showed fairly strongly that hydrolysis could play a large role at this site with its 10-year half-life. Now, focused on the source area, I've sort of changed the y-axis on this top figure into the maximum time in the aqueous phase, and this is incorporating this idea of hydrolysis being sort of a ubiquitous process. And so if you can normalize by that, you can constrain how long the EDB has been in the aqueous phase. And so in the source area, we see these high concentrations of 10 to about 100 parts per billion of EDB. And if we use hydrolysis, we can suggest that the EDB has been in the aqueous phase for 15 years or less. So that means that there has been something preventing it from hydrolyzing, even though EDB and avgas was last used in the 1970s at the site. So that's an interesting process. And it could certainly be a lot less than 15 years, and it probably is, because we have this evidence of the anaerobic processes happening in this zone, and those would also add some additional isotope fractionation. So generally, if we put things on this log scale plot, this is similar to the Rayleigh plot I did before. It's linearized, so it's a log scale on the x-axis. You see this movement from right to left as EDB concentrations go down. We see this nice enrichment of carbon-13 in the residual EDB. So that's a nice indicator that there is some transformation of the EDB occurring. I'm usually fairly reluctant to put isotope data on a Rayleigh plot because there's usually a lot of noise and scatter, but if we group things in this way, source area and down gradient, we really see this nice shift. And I've included here an assumed avgas source that would be in equilibrium with a fresh avgas with an assumed delta 13C value of about minus 30 per mil. So we see this shift as EDB concentrations go down, indicative of degradation, and we think this down gradient part is a steeper slope consistent with hydrolysis. So as I mentioned, we also had an anaerobic biostimulation effort for this project, and that was focused here in the red circled area. And this was a very large-scale pilot that was done in collaboration with Kirtland Air Force Base and the U.S. Army Corps of Engineers. This was a pilot effort that demonstrated that biostimulation could work, and so it's of fair interest. It was targeted solely at the EDB. The approach was taken with a recirculation system, and we would go in multiple phases. The first phase would be to add some tracers and evaluate the distribution of the water that we were recirculating and to set new baseline conditions. And then the second phase would be evaluating biostimulation by adding lactate and nutrients to the water, in that case, diammonium phosphate. And our treatability results suggested that it might not be sufficient to just biostimulate, so we added an extra phase that allowed for some bioaugmentation, so that's introducing exogenous organisms. But we certainly felt that there was evidence that it was occurring at the site in terms of the bromide and the ethane occurring, and we also had some DNA evidence that dehalogenating organisms were present, so we wanted to phase this approach, and then after that we would continue monitoring at the site. So here we're zooming in now on the pilot demonstration site for biostimulation. We had an injection well in the middle, and then we would push the water out radially and 2 extraction wells on either end. Those were pumping at about 10 gallons per minute, and we were injecting at 20 gallons per minute with amended water or tracers as needed. And then we introduced some new groundwater monitoring wells with different distances. So MW2 here in purple on the lower left, that's the closest one. That was a nested well, and so is this one, MW1 above that. Those are both nested wells in shallow and deeper zones. And the blue monitoring wells, those were already existing, with 64 being a shallow well. So we really have 2 or 3 shallow wells very close to our injection well. One thing I'll note is that at 500-foot depth, this is as close as we felt comfortable placing wells. So the extraction wells are about 150 feet apart, and the closest spacing between wells is about 30 feet apart. And the concern there was making sure that the wells were plumb so that the screens where we thought they might be. So as I mentioned, one of the first things we wanted to do was a tracer test. And we actually used 2 tracers in this case. We used a fluorescein dye and deuterium labeled water. This was sort of a belts and suspenders approach, because it was very important that we get data that we could rely upon. And so we used both, and you know, it was comforting that they both came out as similar as they did. So you see here the tracers. This was a 24-hour tracer injection, and then we kept recirculating for another 30 days. The tracer showed up within 5 or 6 days at this near well. And then as you go further along, 64, 1S, you see the tracer show up at later time periods. And again, there's this nice match between the fluorescein data and the hydrogen isotope data. Something you'll also see here is that we did eventually reach our extraction wells with our tracers. They had dispersed quite a bit by then, but what is nice is you actually see this remixing of the tracers from the extraction wells to those near monitoring wells, so that gives good evidence that we are doing a good job of mixing water within the zone. So we felt good moving forward towards doing the biostimulation phase. We were moving water to all these locations, and we thought there would be a good chance of stimulating the organisms. So again, we did biostimulation with lactate and diammonium phosphate. On the left here and on the right, you see these zones. There's this blue zone and then 2 red zones. The blue zone was the addition of the tracers and mixing. Then there was a white zone where we just kind of monitored what was happening in the wells. And then we had our first biostimulation effort here. That was adding the lactate and diammonium phosphate, and we recirculated that for about a month. And then we turned it off the system and monitored EDB and benzene and other contaminants. And then We saw enough success that we thought we should do another biostimulation phase to see if we could stimulate things further and there would be no need for bioaugmentation. So overall, I think you see a great success here. EDB on the left, it started on the order of 100 parts per billion in our zone as we mixed, and you see it sort of tighten up and all the wells kind of show in the same area. And then we turned off the system, the organisms, anaerobic biodegradation occurred, and we moved below the MCL in several cases and certainly a large amount of degradation in the others. And we don't see that matched in the benzene. So benzene was also a contaminant of concern at the site, but like I said before, it was not targeted here, but I'm presenting it because it shows a good sort of base case, a more conservative compound that can still be volatilized, such as the EDB, and to demonstrate that that's not a process that's occurring and affecting our EDB concentrations. And then, like I said, we ran another, after several months, 4 months, we ran another recirculation biostimulation effort with lactate and diammonium phosphate again. And then ultimately, after about a year after we first started treatment, we saw 99.7+% reduction in EDB from our baseline concentrations at the 4 closest monitoring wells, and 3 of the wells were below the EPA MCL, so that was quite successful. But again, it was only targeting the EDB. So I mentioned before, we were very interested in the isotope processes occurring at the site, and here I've shown in green measurements we've taken during the biostimulation effort, the anaerobic biostimulation effort. And you can see that this really starts filling in these gaps between our assumed avgas source and what's happening down gradient. And it also covers the area of the samples we took in our earlier evaluation of natural attenuation. So in some ways, it suggests that the process going from the source to this further down gradient concentrations is consistent with this anaerobic biodegradation with this shallower slope and then a steeper slope once we get to lower EDB concentrations that is consistent with hydrolysis. So this really helped fill in what might be happening at the field site. So overall conclusions regarding EDB at the site. EDB degradation results in isotope fractionation. We saw that in the lab and at the field. And really, this natural attenuation of EDB was apparent at this larger scale field site. Its plume is about 1 mile long, and we saw it. We think hydrolysis is certainly relevant and the lower concentrations, where at the temperatures in New Mexico, the half-life is on the order of a decade. And that can lead to measurable isotope fractionation. And then anaerobic biostimulation was effective for EDB in sort of the source area with a more than 99% reduction in most wells. And then overall benefits to DoD and the community at large, I would say that we're working to develop better tools to evaluate EDB natural attenuation. I certainly think that the isotope analyses that Tomas Kuder and company at Oklahoma were performing really provided a lot of insight into the degradation of EDB at the site. We are getting better knowledge on the degradation mechanisms related to avgas leaks, and I guess this would also relate to historic releases from underground storage tanks with leaded fuels, which have a similar timeline. And we were also demonstrating that sort of anaerobic in situ bioremediation, which we often use for chlorinated solvents, might also be effective for EDB. And that is occurring when there's all these other contaminants of concern, these petroleum hydrocarbons when they're present. And I'll finally note that, we call EDB an emergent contaminant, but we still use it widely, and we've known about its toxicity and in fairly large volumes. So avgas is being used. There are alternatives being explored that, to avoid the use of lead, and hopefully that will also, at that point, lead to further reduction in the use of EDB. And with that, I guess I'll wrap up and open up to questions and see what interesting things people are asking.
Well, thank you very much. This is Mike Cavanaugh again. Very nicely presented and very interesting study. We have a few questions, and people can still submit their questions via the Q&A box on the screen. First question for you, are the compound-specific isotope analyses methods that you use commercially available?
That's a very good question. CSIA is, I'd say, still developing. There are commercial labs that evaluate it for chlorinated solvents. I don't know I'm sure they're able to. I don't know if any are evaluating EDB, but the challenge is that these EDB concentrations we're talking about are so low that you really need a specified method to sort of pre-concentrate that. And Tomas Kuder at Oklahoma has done an excellent job of pursuing methods to get valuable data. One thing I'll note is that our uncertainties were bigger at those lower concentrations. They were on the order of a couple per mil, 2 or 3, but we were fortunate we saw this very large signal. And so, it still was very informative, even though there was less certainty in the isotope measurements.
Great, great. This is a very interesting site, given the tremendous depth to the groundwater, 500 feet. Is the vadose zone going to continue to be a source? What's your conceptual model of what happened at this site?
I think it is still a continuing source for this, and probably as much so the other fuels that may have been released later. There have been a lot of efforts at the site to treat the vadose zone. Another complicating factor there is, as Albuquerque has been conserving its water better, the water table has been rising, so that's actually been challenged for the site as screens become inundated and flooded. And in fact, some of the old vadose zone gas monitoring wells are now being used, I think, as groundwater monitoring wells, so the groundwater has been coming up a lot. But yeah, with 500 feet of vadose zone, I think it's been quite a challenge at the site to understand what's happening.
Yeah, it reminds me of the Williams Air Force Base story, where they had a very large fuel spill there, and it got down to 250 feet, and then the groundwater started rising at 4 feet a year, and an L-NAPL problem became a D-NAPL problem.
I think it's very similar. Well, I don't know if it's a D-NAPL problem, but I think there is a flooded situation there.
With respect to your biostimulation, did you do some lab studies ahead of time to design your pilot test, and also what did you use for bioaugmentation culture? So
we did do a treatability study ahead of time, and in some ways it was discouraging because we didn't see biostimulation was not effective. And I think you might see this a lot, moving things from the lab to the field, that putting it in a bottle does not necessarily represent what might be effective at the field. So that's a challenge. When we used our the helicocoides cultures that we have in the lab here, we were able to stimulate EDB degradation, so we felt confident if we had to introduce that in the field that we would be able to. But we definitely wanted to have a biostimulation phase because we had all this evidence that the organisms were there by DNA analyses, complements of microbial insights, their quantum array chlor analyses, and also we had seen all this aphine and bromine in those source areas. So we were confident that could work, but we wanted to have a backup plan, so to speak.
Mm-hmm, mm-hmm. And what about your bioaugmentation culture? I don't know if you mentioned that.
So we had planned to use a SDC9 culture, but ultimately we didn't need to. I think it's still approved at the site if that's needed, but the biostimulation worked well.
I see. Okay, great. Another question for you: with a large amount of L-NAPL present at the site, and apparently that's the case. I'm not sure you mentioned that, but are you confident that remediation can be effective given the mass transfer limitations dealing with L-NAPL?
I think that's a very good question. We actually found a little bit of L-NAPL at one of our monitoring wells just before we started, and we were able to measure EDB within that L-NAPL, and it was about 20. I want to say it was 20 parts per million by mass, and in equilibrium it was about 400 parts per billion in the aqueous phase. It's hard to say. I think we'd have to see what sort of rebound there is, but as we looked at the data from the field site thus far, there hasn't been much rebound. We suggest, and we think it's important to keep monitoring to see what sort of rebound it occurs, perhaps from the L-NAPL or from outside the treatment zone.
All right, good. Another question regarding this issue of sort of overall remedy for the site. since you observed and documented natural attenuation of EDB, do you think recommending EDB transformation via chemical degradation or base hydrolysis is going to be sufficient to get approval of NA as a part of the remedy?
You know, that's a good question. I'm not sure I know which way they are going to go at the site. You know, if it's a chemical biotransformation or biological. Right, thus far, EDB has been a large driver at the site, and there's a big pump and treat system at the site to sort of collapse this larger plume. And we were fortunate to capture our sort of natural attenuation data before they turned that system on. But my understanding is that they're now trying to collapse the sort of more dilute plume via pump and treat, and then deal with the source area later.
Gotcha. Good. Are there any other contaminants in aviation fuels that you think you need to be worried about? It was interesting to see the benzene contamination continuing. That presumes that there's a continuing source there, which is the LNAPL, I presume.
That is, yeah, I mean, it was a avgas JP4 and JP8 release or leak at the site. So you know, you have a whole wide variety of hydrocarbons, including benzene and toluene, ethylbenzene, xylenes. I think cumene is in there, isopropyl benzene. There's a whole slew of contaminants. I think EDB has been a driver because it has this very low MCL, and because of its physical chemical properties, it can get ahead of the others in terms of its retention in the groundwater and lack of volatilization.
All right, great. Well, good. Well, I think that does it for questions for you, Paul. Maybe we could bring Paul Hatzinger back to the table and see if the two of you, given your work on these two problems, have any overarching comments you'd like to make with respect to addressing some of these emerging contaminants. Is there some sort of general takeaways that you want to share with the audience in that regard, kind of a broader perspective of looking at these emerging contaminants and the expansion of some of the tools we have to address these problems? Paul, are you hopefully still on? Paul Hatzinger?
I am. I'm on, Mike. Yeah, I guess I think the first thing I'd like to do is just give thanks to the CERTUP ESTCP program, because they seem to be the one organization that really gets out in front of a lot of these types of contaminants. And it seems to me that every time we think we've sort of reached the end, and you've been around a while like I have, Mike, and remember when MTBE was the world's biggest problem, and that seemed, and now
unsolvable.
It seemed unsolvable. It was solvents were unsolvable, and where are we now in the last 5 years? Well, now it seems like everything is PFAS, and sort of ESTCP is moving forward and doing a lot of work in that area. But I think that being said, some of these contaminants are harmful at very low concentrations. And as I go back and think about school and toxicology, we really didn't worry about things at parts per trillion levels, at least when I was in graduate school looking at environmental tox. Right. But it seems today some of these compounds, and the two that we talked about today, have extremely low risk levels and levels of concern. And with EDB, I think, and Ron Falta did some work a number of years ago, but I think that you would find that there are an awful lot of sites that have EDB well above MCLs. At least as of 10 years ago, Ron Falta at Clemson did a survey in South Carolina, and had sites, something like 50% of the sites they looked at least one hit that was, 10 times the MCL. And yet, right, we're not very concerned about it. I think we, in part because the methods that we use to test for everything else, our 8260, is not nearly sensitive enough to detect EDB at levels where we should be looking at it. And I think trichloropropane, that those data for me from from the California, since they've established the California MCL, were pretty eye-opening, that they've already, in the first 3 quarters of sampling, have 500 and some odd exceedances in drinking water, of which more than half right now are not being treated. So, I don't know what the whole lesson is there, but I think in part it's that there are still some bad actors out there besides PFAS that are creating problems. I think 1,4-dioxane also falls in this category. And but there's some good research going on both in the lab and the field. A lot of it's sort of ESTCP funded to really look at how practitioners can actually get out and treat these things in a lot of different approaches, be it vadose, trichloropropane, or groundwater EDB, or 1,4-dioxane in these areas. And so those are still things that really should be on our radar, but a lot of times I don't think they are.
Well, that was a great summary about some of the challenges with emerging contaminants, and I'll make sure Andrea knows about your shout out about CERTIP and ESTCP. That's good work. That sounds great. Paul, Koster von Groos, do you have any sort of overarching thoughts yourself on this topic?
I mean, in a lot of ways, I would echo what Paul Hatzinger said. And specifically, I guess, to some of the data I was presenting, I think I would also like to reinforce that the isotope data can be very powerful in understanding what might be going on at a site when there is a lot of complexity. In terms of, in our case, we looked at carbon isotopes, but there's certainly power in also looking at the other isotopes, chlorine or hydrogen isotopes or bromine. So as those tools develop, I think you might see value in examining those as well.
Great. Well, that's a good point. Well, listen, thanks to both of you for really outstanding presentations. Let me just end with a couple of notes. The next webinar for this series is on Thursday, June 6th in the Weapons System and Platforms Program area on environmentally friendly and high-performance polysiloxane top coats for DoD aircraft and ground support equipment. Registration is open, so please visit the webinar webpage and register for that and other future webinars. And before I conclude, I want to remind everybody that the audio and copy of the presentation of today's session will be archived on the ESTCP webinar webpage, in CERTIP webpage, in case you would like to refer to them in the future. We'd appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. So this concludes today's webcast. Again, thanks to both of the speakers, and thank you all, and have a good day.
Thanks, Mike.
Thank you.